Somewhere in the darkness between the stars, something is moving. It has no light, no surface, no warning beacon of any kind. It is invisible against the blackness of space, and it is heading toward us. A black hole, one of the most extreme objects the universe has ever produced, is on a collision course with our solar system. You won't see it coming. No telescope will catch it until it's already close enough to have begun rewriting the orbits of everything we've ever known. The planets will start to wander, the sun will feel the pull, and Earth, our fragile, spinning home, will face forces that make every catastrophe in human history look like a minor inconvenience. Tonight, we explore what would actually happen, step by terrifying step, when the ultimate cosmic predator enters our neighborhood. This is not science fiction, this is physics. Before we can understand what happens when a black hole enters our solar system, we need to truly understand what a black hole is. Not the Hollywood version, not the vague idea of a cosmic vacuum cleaner sucking up everything around it, but the real, physics-grounded, deeply strange object that scientists have spent over a century trying to fully comprehend. A black hole is, at its most fundamental level, a region of space-time where gravity has become so intense that nothing, not matter, not radiation, not even light, can escape once it crosses a critical boundary called the event horizon. This boundary isn't a physical surface. There is no wall, no membrane, nothing you could touch or see. It is simply a mathematical threshold in the geometry of space-time, beyond which the escape velocity, the speed you would need to travel to break free from the gravitational pull, exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. The concept emerged from Einstein's general theory of relativity, published in 1915. Karl Schwarzschild, a German physicist serving on the Russian front during World War I, solved Einstein's field equations just months after they were published and found a solution that described the geometry of space-time around a perfectly spherical, non-rotating mass. His solution contained something strange. At a specific radius now called the Schwarzschild radius, the geometry became singular. Later physicists realized this radius corresponds to the event horizon of what we now call a black hole. At the center of a black hole, at least in the mathematics of classical general relativity, lies a singularity, a point of infinite density where the known laws of physics break down completely. Whether singularities actually exist in nature, or whether they're a signal that our current theories are incomplete, is one of the deepest unsettled questions in theoretical physics. Quantum gravity, the not yet fully developed theory that would unite quantum mechanics and general relativity, is expected to resolve what really happens at the center of a black hole. But we don't have that theory yet. What we do have is extraordinary observational evidence that black holes are real. The detection of gravitational waves by the LIGO and Virgo observatories beginning in 2015 has given us direct evidence of black hole mergers, pairs of black holes spiraling together and colliding in events that release more energy in a fraction of a second than the Sun will radiate over its entire 10 billion year lifetime. The Event Horizon Telescope collaboration produced the first direct image of a black hole's shadow in 2019, imaging the supermassive black hole at the center of the galaxy M87, with a mass of 6.5 billion solar masses. In 2022, they imaged Sagittarius A*, the supermassive black hole at the center of our own Milky Way galaxy. black holes come in several categories defined by their mass. Stellar mass black holes form when massive stars, those with more than roughly 20 to 25 times the mass of the Sun, exhaust their nuclear fuel and collapse. The core collapse triggers a supernova explosion, and if the remaining core is massive enough, it forms a black hole rather than a neutron star. These stellar mass black holes typically range from about 3 to a few tens of solar masses. Intermediate mass black holes, ranging from hundreds to hundreds of thousands of solar masses, are theorized to exist and may have been detected in some observations, but they're less well understood, and their formation pathways are still being worked out. Supermassive black holes, ranging from millions to billions of solar masses, lurk at the centers of virtually all large galaxies, including our own. How they formed is one of the outstanding questions of astrophysics. More recently, a fourth category has gained scientific attention: primordial black holes. These hypothetical objects would have formed in the extremely dense early universe, fractions of a second after the Big Bang, from density fluctuations rather than stellar collapse. Primordial black holes could have masses ranging from asteroid-sized to stellar mass, and some researchers have proposed that they might constitute a portion of the dark matter that makes up roughly 27% of the universe's mass-energy content. For our thought experiment tonight, we need to decide what kind of black hole is heading toward our solar system. This choice matters enormously because a stellar mass black hole, say 5 to 10 solar masses, would behave very differently from a supermassive monster. We're going to focus primarily on a stellar mass black hole because this is the most scientifically plausible scenario for an interloper approaching from the galaxy. These objects are thought to number in the billions within the Milky Way, and while an encounter with our solar system is extraordinarily unlikely, it is at least within the realm of physical possibility. Where needed, we'll note how different masses would change the story. So, a black hole, perhaps 5 to 10 times the mass of the Sun, dark and invisible against the backdrop of space, is moving through the galaxy on a trajectory that brings it into our solar system. What happens next? The first challenge humanity would face in our scenario isn't survival, it's detection. A stellar mass black hole wandering through the galaxy would be, in the most literal sense, invisible. It emits no light of its own. Unlike a star, it produces no radiation from nuclear fusion. If it isn't actively accreting material, pulling in surrounding gas and dust that heats up and glows as it falls in a dormant black hole, drifting through interstellar space is essentially undetectable by conventional astronomical methods. This is a genuinely unsettling aspect of the scenario. The universe may contain billions of stellar mass black holes that formed when massive stars died, and we have directly detected only a small fraction of them, those that happen to be in binary systems with companion stars, or those that were involved in gravitational wave events. The isolated ones, wandering alone through the dark between the stars, are largely invisible to us. How far away would an approaching black hole need to be before we could detect it? The answer depends strongly on the detection method. Direct imaging is essentially impossible for a dormant black hole against the darkness of space. There is no surface to see, no light being emitted. The only possibility of direct detection would be gravitational lensing, the bending of light from background stars as the black hole's gravity curves space-time around it. If a black hole passed in front of a distant star from our perspective, the star would appear to brighten as the black hole's gravity focused its light toward us. This is called gravitational microlensing, and it's a technique that astronomers already use to search for dark, compact objects. However, microlensing events are transient, brief, and require the black hole to be almost precisely aligned between us and a background star. Detecting a specific approaching black hole through microlensing would require extraordinary luck. A more practical detection method would be gravitational measuring the perturbations the black hole causes to the orbits of bodies within our solar system as it approaches. Long before a stellar mass black hole reached the inner solar system, its gravity would begin to subtly alter the orbits of the most distant, most gravitationally sensitive objects. The extreme trans-Neptunian objects that orbit in the far outer solar system, and the hypothetical planet 9 that some astronomers believe lurks in the distant reaches of our solar neighborhood. If such perturbations were detected and recognized for what they were, not an unknown planet, but an approaching compact object that might provide years or decades of warning. But the analysis would require careful and sustained observation, and distinguishing the gravitational signature of an approaching black hole from other possible explanations would be challenging. In our scenario, let's say humanity gets warning. Perhaps astrometric observations, precise measurements of stellar positions, detect that a dark object is deflecting the light of background stars in a way consistent with a compact mass of several solar masses. Perhaps perturbations in the orbits of distant Kuiper belt objects provide a gravitational clue. Either way, at some point in this scenario, the astronomical community recognizes that something massive and dark is approaching. How much warning time would we have? If the black hole is approaching at a typical stellar velocity relative to our solar system, perhaps 20 to 30 miles per second, which is a common relative velocity between stars in our galaxy's neighborhood, and it's detected when it's perhaps 1 to 2 light years away, we might have thousands of years of warning. Long enough, in principle, for a sufficiently advanced civilization to contemplate response, useless, in practice, for any civilization at our current level of technological development. At closer range, say, a few hundred astronomical units, roughly the distance of the inner Oort cloud, the perturbations to solar system objects would become unmistakable. At this point, with the black hole perhaps a few thousand years away at typical stellar velocities, the gravitational effects on the outer solar system would already be measurable and significant. The psychological impact on humanity of confirmed knowledge that a black hole was approaching our solar system is difficult to overstate. Nothing in human experience or history provides a framework for comprehending this kind of cosmic threat. Religious, philosophical, and psychological responses would be as varied and chaotic as humanity itself. Some would see fulfillment of apocalyptic prophecy. Others would call for coordinated scientific response. Most would simply struggle to make the abstract cosmic threat feel real against the backdrop of everyday life. But whether or not we knew it was coming, the black hole would continue its approach, and as it drew closer, the effects on our solar system would accelerate from subtle to dramatic to catastrophic. Long before a stellar mass black hole got anywhere near the planets, it would pass through the outer reaches of our solar system, a vast, diffuse shell of icy bodies called the Oort cloud, and its passage through this region would trigger the first of the cascading catastrophes, one with direct consequences for Earth. The Oort cloud is the solar system's most distant and most poorly understood region. It extends from roughly 2,000 to perhaps 200,000 astronomical units from the Sun, an astronomical unit being the average Earth-Sun distance, about 93 million miles. The outer edge of the Oort cloud is only about a quarter of the distance to the nearest star. This vast spherical shell is thought to contain trillions of cometary bodies, icy objects, ranging from house-sized to perhaps tens of miles across, left over from the formation of the solar system billions of years ago. Under normal circumstances, most Oort cloud objects spend their entire existence in stable, near-circular orbits far from the sunday. Occasionally, gravitational perturbations from passing stars or tidal forces from the galaxy nudge some of these objects onto highly elongated orbits that carry them into the inner solar system as long-period comets. These events are rare on human timescales. A stellar mass black hole passing through or near the Oort cloud would be categorically different from a passing star. Its gravitational influence would be as strong as or stronger than the Sun itself, and its passage would be relatively fast, not slow enough to allow the Oort cloud's gentle orbital adjustments that a gradual influence might produce, but fast enough to deliver sudden, dramatic perturbations to trillions of icy bodies at once. The result would be something astronomers call a comet shower, but on a scale that would dwarf anything that has occurred in the solar system's history. Trillions of cometary nuclei would have their orbits fundamentally altered. A large fraction would be ejected from the solar system entirely, sent off into interstellar space by the black hole's overwhelming gravity. But a significant fraction, potentially billions of objects, would be kicked onto trajectories that send them plunging inward toward the Sun and the planets. This comet shower would take time to arrive at Earth. Oort cloud objects have very long orbital periods, hundreds of thousands to millions of years for the most distant ones. But those kicked from the inner Oort cloud, perhaps from tens of thousands of astronomical units away, might arrive in the inner solar system within thousands of years of the perturbation. As the black hole continued to approach, progressively closer Oort cloud objects would be perturbed, sending waves of inbound comets on increasingly short arrival timescales. For Earth, this comet shower would represent an unprecedented bombardment. Current estimates suggest Earth is struck by a significant impactor, one large enough to cause regional devastation perhaps once every few million years on average, and by a civilization-ending impactor perhaps once every 100 million years. During a Oort cloud disruption by an approaching black hole, the rate of comet impacts could increase by orders of magnitude. The consequences for Earth of even a single large comet impact are sobering. The Chicxulub impactor that killed the non-avian dinosaurs 66 million years ago was probably 10 to 15 miles in diameter. The energy released was equivalent to billions of nuclear weapons. The immediate blast effects, global firestorms, and subsequent impact, winter caused by debris and sulfur aerosols, blocking sunlight for months to years, drove a mass extinction that eliminated roughly 75% of all species on Earth. In a comet shower driven by an approaching black hole, Earth could face multiple such impacts over centuries and millennia. The planet might survive the bombardment as a planet, its orbit unchanged, its core intact, but as a habitat for complex life, the sustained bombardment would be catastrophic. Even if humanity somehow avoided direct hits through technology, the climate disruption from multiple large impacts would make agriculture and organized society essentially impossible for extended periods. But the comet shower is just the opening act. The black hole is still approaching, and with each passing century, its gravitational effects reach further into the solar system, growing stronger, more dramatic, and more inescapable. As the black hole draws closer, entering the realm of the giant planets, Perhaps at distances measured in hundreds or tens of astronomical units, its gravitational influence begins to affect the most massive objects in the outer solar system. Neptune, Uranus, Saturn, Jupiter, these gas and ice giants, which contain the vast majority of the solar system's mass outside the Sun, begin to respond to a gravitational force that is now comparable to or greater than the Sun's influence on them. Let's ground this with some perspective on scale. Neptune orbits at about 30 astronomical units from the Sunday, Saturn at about 9.5, Jupiter at about 5.2. These planets have been in essentially stable orbits for over 4 billion years, their positions maintained by the careful gravitational choreography of the solar system, Jupiter's enormous mass influencing the others, their gravitational interactions long since settled into stable resonances and patterns. A stellar mass black hole moving through or near this region disrupts this choreography with brutal efficiency. The gravitational perturbations it delivers to the outer planets are not subtle nudges. They are powerful kicks that alter orbital energies, inclinations, and eccentricities in ways the solar system has never experienced. The specific outcomes depend critically on the trajectory of the black hole, how close it passes to each planet, at what speed, and from what direction. Gravitational encounters between celestial bodies can have wildly different outcomes depending on these parameters. In some scenarios, a planet might be ejected from the solar system entirely, sent on a hyperbolic trajectory out into interstellar space. In others, a planet's orbit might be dramatically altered, made more elliptical, tilted relative to the solar plane, or shifted inward or outward. In rare geometric configurations, a planet might even be captured into orbit around the black hole itself, though this outcome is statistically unlikely for a fast-moving interloper. Neptune, being the outermost major planet, would feel the black hole's influence first. If the black hole passes within perhaps 50 to 100 astronomical units of the Sun, Neptune's orbit would be significantly perturbed. Its roughly circular orbit might be stretched into a much more elliptical one, causing it to swing much closer to the Sun at its closest approach or much further away at its most distant point. Alternatively, Neptune might be ejected entirely from the solar system, escaping the Sun's gravity and becoming a rogue planet drifting through interstellar space. Either outcome has profound downstream consequences. Neptune currently plays an important role in shepherding the Kuiper Belt, the region of icy bodies beyond Neptune that includes Pluto. Neptune's gravity maintains the structure of the Kuiper Belt and prevents many of its objects from entering the inner solar system. Remove Neptune or radically alter its orbit, and the Kuiper Belt destabilizes, sending a new wave of icy bodies raining inward. But it is Jupiter that matters most for Earth's long-term habitability. Jupiter, with a mass more than twice that of all other planets combined, acts as something of a gravitational shield for the inner solar system. Its enormous gravitational influence deflects many long-period comets that would otherwise strike the inner planets, sending them onto different trajectories. The famous Shoemaker-Levy 9 comet, which dramatically crashed into Jupiter in 1,994 inches, a series of impacts that left marks larger than Earth, illustrates this shielding effect. Without Jupiter, Earth would likely have experienced far more cometary impacts throughout its history. If the approaching black hole significantly perturbs Jupiter's orbit, making it more elliptical or tilting it significantly relative to the solar plane, Jupiter would lose its ability to act as Earth's gravitational protector, Worse, an altered Jupiter might actually begin destabilizing the inner solar system through its changed gravitational interactions with Mars, Earth, Venus, and Mercury. Computer simulations of solar system dynamics have shown that even small changes to Jupiter's orbital parameters can, over millions of years, lead to chaotic outcomes in the inner solar system. An abrupt, large perturbation from a passing black hole would produce much more immediate and dramatic consequences. The scenario of Jupiter itself being ejected from the solar system possible if the black hole passes close enough with the right geometry is particularly alarming from Earth's perspective. The inner solar system would lose its gravitational anchor and protector simultaneously. The remaining planets, suddenly unshielded and with their mutual gravitational interactions changed, would enter a chaotic orbital dance that could play out in various ways, but most of them bad for any life on Earth. Saturn's rings and the complex system of small bodies throughout the outer solar system would be extensively disrupted by these gravitational perturbations. Asteroid families that have remained in stable configurations for billions of years would be scattered, sending new streams of rocky debris inward. The asteroid belt itself, whose current structure is maintained by Jupiter's gravity through orbital resonances, would be destabilized. The visual spectacle of these changes, if anyone survived to watch, would be extraordinary. Planets in highly elliptical orbits would move noticeably across the sky in ways that no human has ever observed. Comets would become frequent, bright visitors. The night sky would be transformed, but these are astronomical timescales, unfolding over years to centuries depending on the black hole's velocity. Meanwhile, something else would be happening that operates on much shorter timescales. The black hole's gravity would be disturbing space itself in ways that travel at the speed of light. One of the most extraordinary consequences of a black hole's close passage through our solar system would be the production of gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light, carrying energy away from the interacting system. Einstein predicted gravitational waves in 1916 as a consequence of his general theory of relativity. He initially doubted they were physical, thinking they might be mathematical artifacts, but later concluded they were real. For decades after his prediction, gravitational waves remained theoretical, because detecting them required measuring distortions in spacetime of unimaginably small magnitude. The LIGO detectors that first detected gravitational waves in 2015 measured displacements of spacetime smaller than 1,000th the diameter of a proton. Those 2015 detections came from black hole mergers at cosmological distances billions of light years away. The gravitational waves they produced, by the time they arrived at Earth, had been diluted to near imperceptibility. A stellar mass black hole passing through our solar system would be infinitely closer, and the gravitational waves it generated would be correspondingly stronger, though still not destructive in the conventional sense. As the black hole interacts gravitationally with the Sun and the planets, it forms a dynamic system. Any system of massive bodies accelerating relative to each other produces gravitational waves. The energy carried by these waves must come from somewhere. It comes from the orbital energy of the interacting bodies. In a close flyby, the gravitational wave emission could be measurable and significant. What would humanity experience from stronger than usual gravitational waves? In the first 2015 detection event, space-time stretching amounted to a fraction of the diameter of an atomic nucleus across the entire 4-kilometer length of the detector arms. Even with a nearby black hole, gravitational waves would not be directly perceptible to human senses. You would not feel the space-time stretching and compressing as the waves passed through you. But sensitive instruments, and by this point in our scenario, humanity would presumably have deployed every available sensor to monitor the approaching threat, would detect dramatic and rapidly varying gravitational wave signals as the black hole maneuvered through the solar system. These gravitational wave signals would be scientifically extraordinary. They would give astronomers a real-time picture of the black hole's mass, trajectory, and even spin. The angular momentum of a rotating black hole affects the gravitational wave signal in characteristic ways. In a different context, such data would be the most valuable astronomical observation in history. In our catastrophic context, the gravitational wave data would tell humanity exactly what it was facing and where the black hole was heading. It would confirm the worst predictions, and it would provide a countdown of sorts not to impact, since a black hole passing through the solar system might not physically collide with anything, but to the closest approach that would define the ultimate severity of the gravitational disruption. There is another gravitational effect worth noting: tidal forces. We are familiar with tidal forces from the Moon's effect on Earth. The Moon's gravity pulls slightly more strongly on the near side of Earth than the far side, creating the tidal bulge that drives our ocean tides. Any massive object creates tidal forces on extended bodies in its vicinity. A stellar mass black hole passing through the solar system would create tidal forces on every planet and moon it passed near. For most scenarios, these tidal forces would be significant, distorting the shapes of planetary bodies, generating heat through tidal flexing in moons and planets, and in extreme close-approach scenarios, potentially disrupting smaller bodies entirely. For Earth specifically, enhanced tidal forces could increase volcanic activity, trigger earthquakes, and cause dramatic oceanic tides. The famous process, called spaghettification, where an object falling into a black hole is stretched into a thin strand by extreme tidal forces, would not occur for Earth unless it passed extremely close to the event horizon. For a stellar mass black hole with an event horizon only a few miles in diameter, Earth would need to approach within a few 100,000 miles to experience spaghettification. At that distance, the gravitational effects on Earth's orbit would already be catastrophic, long before tidal disruption became the dominant concern. The gravitational drama playing out in the outer solar system is prologue to what happens when the black hole's influence reaches the inner planets. Mercury, Venus, Earth, and Mars, the terrestrial planets, have been in stable orbits for over 4 billion years. Their current configuration is the survivor of the violent early solar system, settled into a gravitational equilibrium that has persisted through billions of years of evolution. An approaching stellar mass black hole threatens to destroy that equilibrium permanently. The inner planets are more tightly bound to the Sun than the outer giants. They orbit faster, experience stronger solar gravity, and in some sense have more resistance to perturbation. But they are also much less massive than Jupiter and Saturn. The gravitational interactions that would play out as the black hole approached would be complex, chaotic, and ultimately unpredictable in their precise details. What is predictable are the categories of possible outcomes: orbital resonances between the terrestrial planets, delicate gravitational synchronizations that have kept them in stable, non-intersecting orbits would be broken. Once resonances break, the planets can begin to interact gravitationally in ways that were previously forbidden. Mars, the least massive of the inner planets and the most easily perturbed, might see its orbital eccentricity, how elliptical its orbit is, increase dramatically, potentially leading to close approaches with Earth or Venus. Computer simulations of solar system dynamics have actually identified scenarios in which Mars's orbital eccentricity could increase through purely internal perturbations over billions of years, potentially leading to a collision between Mercury and Venus, or the ejection of Mercury from the solar system. These are low-probability outcomes on geological timescales under normal conditions. The passage of a stellar mass black hole would accelerate and amplify these instabilities dramatically. Earth itself could see its orbit altered in ways that directly affect its habitability well before any physical catastrophe. Even relatively modest changes to Earth's orbital eccentricity, how elliptical its orbit is, can have dramatic climate consequences. During ice ages, Milankovitch cycles, periodic changes in Earth's orbital parameters, drive swings between glacial and interglacial periods. These are small changes compared to what a passing black hole might impose. If Earth's orbit became significantly more eccentric, the range of temperatures experienced over a year would increase dramatically. A much more elliptical orbit would mean that Earth spent part of its year much closer to the Sun, potentially hot enough to boil oceans, and part much further away, potentially cold enough to freeze them. Life on the surface would face seasonal temperature extremes far beyond anything in Earth's history. Changes to Earth's orbital inclination. The tilt of its orbit relative to the original solar plane would alter the character of seasons and could affect climate stability in less obvious ways. The complex gravitational interactions between all the planets, once disrupted, could lead to rapid changes in these orbital parameters over timescales of decades to centuries, rather than the millions of years that Milankovitch cycles operate on. The Moon adds another dimension to Earth's response to this gravitational perturbation. The Moon has a stabilizing influence on Earth's axial tilt, the angle between Earth's rotation axis and its orbital plane. Currently, Earth's axial tilt is about 23.5 degrees, and it varies only slightly over long timescales precisely because the Moon stabilizes it. This stable axial tilt is thought to be important for Earth's climate stability over geological time. Perturbation of the Earth-Moon system by an approaching black hole could alter the Moon's orbit, reducing its stabilizing influence. If Earth's axial tilt began to vary widely as Mars's does, because Mars lacks a large moon, the character of Earth's seasons would become chaotic and unpredictable. Extreme axial tilts could lead to polar regions facing the Sun continuously for extended periods, while equatorial regions froze, completely disrupting the climate patterns that support life. While all of this gravitational disruption was unfolding on timescales of decades to centuries, human civilization would be under extraordinary stress. Agriculture would fail as climate patterns changed. Infrastructure built for stable coastal conditions would be threatened by changed ocean tidal patterns. The global economy, already the product of fragile supply chains and interdependencies, would collapse under the weight of simultaneous agricultural failure, infrastructure damage, and the psychological shock of an existential cosmic threat with no possible defense. Throughout our scenario, we've focused primarily on the effects on the planets, but the Sun, the dominant mass of the solar system, containing 99.86% of all the solar system's mass, would be profoundly affected by the black hole's approach as well. A stellar mass black hole of, say, 8 solar masses represents a significant fraction of the Sun's mass. As it approached, the gravitational interaction between the black hole and the Sun would become increasingly powerful. The Sun is not a rigid body, it is a fluid sphere of plasma, and it responds to tidal forces. As the black hole approached, it would raise tidal bulges on the Sun's surface, far more powerful than the tides the Moon raises on Earth. The Sun's plasma would be distorted toward the approaching object. If the black hole passed close enough within perhaps a few astronomical units, the tidal distortion of the Sun could become dramatic and potentially disruptive. Solar activity would almost certainly be affected. The convective zone of the Sun, the outer layer where heat is transported upward by bubbling plasma, is sensitive to perturbations. Enhanced tidal forces could dramatically intensify solar activity, triggering more frequent and powerful solar flares and coronal mass ejections. These bursts of plasma and radiation, if directed toward Earth, can disrupt power grids, damage satellites, and expose unshielded organisms to harmful radiation. An intensified, chaotic Sun would bombard the solar system with radiation and charged particles far exceeding anything in recorded solar history. The question of whether the black hole could capture the Sun, essentially stealing it from its current position and incorporating it into a black hole system, depends entirely on the orbital mechanics of the encounter. A direct collision between a stellar mass black hole and the Sun is extraordinarily unlikely. Space is mostly empty, and the Sun is a small target on cosmic scales. But a close flyby that resulted in mutual gravitational capture, the two objects entering orbit around each other, would be one of the most dramatic possible outcomes. If the Sun and the black hole were mutually captured, they would form a binary system, a star and a black hole orbiting their common center of mass. This is not a science fiction scenario. Such binary systems exist throughout the galaxy and are observed as X-ray binaries when the black hole is actively accreting material from the companion star. In our case, the Sun would be the companion star, and as the black hole drew off solar material, the Sun would lose mass and its energy output would change. For the planets, mutual capture of the Sun and black hole would be catastrophic in a different way than a simple flyby. The new binary system's gravitational landscape would be nothing like the current solar system. Planets would be flung into wildly chaotic orbits under the combined and changing gravity of two massive objects. Most planetary orbits would become unstable on timescales of years to decades. The likelihood of Earth maintaining a habitable orbit through this process would be essentially zero. Even in the scenario where the black hole makes a close flyby without capture, the perturbation to the Sun's trajectory through space would be significant. The Sun would be deflected from its current path through the galaxy, affecting its long-term orbital dynamics around the galactic center in ways that are ultimately inconsequential for any surviving civilization, but which are fascinating markers of the encounter's cosmic scale. There is also the question of what happens if the black hole passes close enough to begin accreting solar material. When matter falls toward a black hole, it doesn't fall in directly unless it's on a precisely radial trajectory. Usually, material spirals inward, forming an accretion disk, a flat, rotating structure of hot gas orbiting the black hole and gradually falling in. Accretion disks are among the most luminous objects in the universe. As matter heats up through friction and gravitational compression, it radiates enormous amounts of energy across the electromagnetic spectrum, including intense X-rays. If the black hole began accreting material stripped from the Sun, it would cease to be invisible. An accretion disk would form and glow brilliantly, potentially outshining the Sun at its brightest. The radiation environment in the inner solar system would intensify dramatically as X-rays and gamma rays poured from the accretion disk. For any life on Earth's surface, this radiation would be deadly, overwhelming any ozone layer protection and delivering doses far beyond what biological organisms can survive. Let us now explore the most dramatic phase of our scenario, the black hole's closest approach to Earth itself. The specific outcomes depend on how close the encounter is, and the range of possibilities runs from merely catastrophic to absolutely final. Begin with the least extreme scenario. The black hole passes through the solar system, but no closer to Earth than, say, 10 to 20 astronomical units, roughly the distance to Saturn or Uranus. At this distance, the black hole's direct gravitational effect on Earth would be significant but not immediately physically destructive. Earth's orbit would be substantially altered. As we discussed in the previous chapter, the Moon's orbit might be destabilized, solar activity would be enhanced, but Earth itself would survive as a planet, though its future as a hospitable environment for life would be deeply uncertain. Now consider a closer passage. The black hole approaches within 1 to 2 astronomical units, roughly the distance from the Sun to Earth or Mars. At this distance, the gravitational disruption becomes far more severe and direct. Earth's orbit could be dramatically altered in a matter of days or weeks. The tidal forces on Earth would be intense enough to cause severe geological disruption, earthquakes, and volcanic eruptions on a global scale, far exceeding anything in recorded history. The oceans would respond dramatically to the changing gravitational landscape. Tidal forces would create enormous waves, not tsunamis in the traditional sense, but permanent distortions of the ocean surface that could be hundreds of feet above normal sea level on the side facing the black hole and correspondingly lower on the opposite side. As the black hole moved, these tidal bulges would sweep across the oceans, flooding coastal regions and then receding in violent surges. The atmosphere would be similarly disturbed. Air pressure variations driven by gravitational anomalies would create extraordinary weather events. Wind patterns would be disrupted globally. The temperature distribution of the planet, already stressed by orbital changes, would become chaotic. At this distance, something else remarkable would happen. Earth's sky would change. The black hole itself would still be invisible, but the material being heated as it accreted from the solar wind and potentially from material pulled off the surfaces of inner planets would create a faint but growing luminescence in its vicinity. The sky would show a region of abnormal brightness, perhaps accompanied by rings of light from gravitationally lensed starlight bent around the black hole's event horizon. Move closer still, a passage within Earth's own orbital radius, inside 1 astronomical unit from the Sun, and we approach scenarios where Earth's fate is essentially sealed in the short term. The gravitational forces at this distance would be overwhelming. Earth's crust would flex so dramatically under tidal forces that volcanic activity would become global and continuous. The oceans might partially escape into space if the disruption were extreme enough, as molecules in the upper atmosphere exceed escape velocity in the churned gravitational environment. The absolute closest approach scenario, the black hole actually passing through Earth's own neighborhood within a few million miles, would produce forces that dwarf anything in the planet's geological history. The tidal differential across Earth's diameter would be powerful enough to begin tearing the planet apart structurally, fracturing the crust into fragments, separating the mantle from the core, ultimately producing what astronomers call a tidal disruption event. though usually this term applies to stars being disrupted by supermassive black holes. The remnants of Earth would be drawn into a debris stream, spiraling toward the black hole's event horizon. The planet would cease to exist as a coherent body. But here is the counterintuitive truth that surprises most people. In the vast majority of plausible scenarios, Earth would not actually fall into the black hole. The event horizon of a stellar mass black hole is tiny for a 10 solar mass black hole. The Schwarzschild radius is about 30 miles. That is a diameter of 60 miles. Earth is a target roughly 8,000 miles across, orbiting in a solar system that spans billions of miles. A passing black hole is extraordinarily unlikely to score a direct hit on Earth. This is an important point to hold. The black hole's danger to Earth comes almost entirely from gravitational disruption, orbital chaos, tidal forces, destabilization of the climate system, rather than from being physically consumed. The black hole doesn't need to touch Earth to destroy it. Gravity is its weapon, and gravity reaches across the entire solar system. Given the scale of catastrophe we've described, comet showers, destabilized orbits, enhanced solar activity, gravitational tidal disruptions, is there any scenario in which life on Earth, or anywhere in the solar system, survives the passage of a black hole? Let's start with the most optimistic scenario. The black hole passes through the outer solar system, close enough to significantly perturb the outer planets, but not close enough to directly devastate the inner system. In this case, the most significant immediate threat to Earth would be the comet shower generated by Oort cloud disruption. This bombardment would unfold over centuries to millennia, providing time for impacts to occur, but potentially leaving intervals between major events. If no civilization-ending impact struck Earth in the near term, and if Earth's orbital changes were not immediately catastrophic, say, a modest increase in eccentricity that changed climate patterns, but did not produce conditions outside the range of biological survival, then life might continue, severely stressed but not extinct. Some species would inevitably be lost. Agricultural civilizations would be devastated by climate disruption, but the biological substrate of life might persist, particularly in the ocean depths and underground environments that are buffered from surface conditions. Human civilization, under this relatively optimistic scenario, would face challenges unlike anything in its history. Agricultural disruption would cause famines. Climate instability would make long-term planning nearly impossible. The psychological burden of knowing an existential threat had passed through the solar system and that its effects would continue unfolding for centuries would be enormous. But with sufficient warning time and preparation, aspects of technological civilization might survive, particularly if space-based habitats were developed. For life more broadly, the resilience demonstrated by terrestrial biology through 5 mass extinction events suggests that some forms of life would survive even quite severe scenarios. Extremophiles organisms that thrive in conditions lethal to most life are found in the deep ocean, in solid rock miles underground, in highly acidic or alkaline environments, in conditions of extreme radiation. These organisms would be the last holdouts of Earth's biosphere in a severely disrupted world. There is also the question of whether Mars or other solar system bodies could harbor surviving life. Mars, while currently uninhabitable on its surface, might have subsurface microbial life sheltered from radiation by kilometers of rock. A gravitational disruption that altered Mars's orbit might not affect its subsurface environment significantly, depending on the magnitude of the disruption. Similarly, the subsurface oceans thought to exist beneath the ice shells of moons like Europa, Enceladus, and possibly others represent environments buffered from surface conditions. If life exists there, which we don't know, its survival through a gravitational encounter might depend primarily on whether the moon itself survived as a coherent body. What about human survival in a more extreme scenario? If sufficient warning time were available decades to centuries, the most technologically capable response would be to develop space habitats capable of supporting human populations independent of Earth's surface. Underground bases, space stations, or colonies on other worlds in stable orbits would provide refuges that might survive even significant disruption of Earth's surface conditions. But we should be honest about the limits of this optimism. Creating self-sustaining space habitats capable of supporting human populations through centuries of solar system disruption would require technological capabilities and resources far beyond anything currently available to our ball. Civilization. The window between detection and impact, the distribution of resources needed, and the sheer scale of the engineering challenge makes survival scenarios for significant human populations contingent on preparation that we are nowhere near having done. The honest scientific assessment is that for any passage close enough to dramatically alter the inner solar system, the probability of complex life surviving on Earth's surface in any recognizable form is very low. Life might persist in protected environments, but human civilization as a functioning, spacefaring entity would almost certainly not survive a close encounter with a stellar mass black hole. Having thoroughly frightened ourselves with the consequences of a black hole entering our solar system, let's take a step back and ask how likely this actually is. Because the honest scientific answer provides significant comfort, though perhaps not absolute reassurance. The Milky Way galaxy is approximately 100,000 light-years in diameter and contains somewhere between 200 and 400 billion stars. Estimates suggest it may also contain roughly 1 billion stellar mass black holes, formed from the death of massive stars throughout the galaxy's 3 billion year history. That sounds like a lot of black holes, but consider the scale of the galaxy against which they're distributed. If you modeled the Milky Way as a disk roughly a kilometer in diameter, about 0.6 miles, each black hole would be represented by a single grain of sand. The solar system, on the same scale, would be about the size of a single hydrogen atom. The distances between objects in the galaxy are staggering, and the probability of any two specific objects encountering each other is extraordinarily small. The Sun completes one orbit of the Milky Way roughly every 225 to 250 million years. In the 4.5 billion years of the solar system's existence, it has completed about 18 to 20 galactic orbits. During this time, the probability of a stellar mass black hole passing close enough to the solar system to cause significant gravitational disruption closer than, say, 1 light-year has been estimated at less than 1 in several million per billion years of solar system existence. To put it another way, if you sat down and watched the solar system for the entire 8 billion year age of the universe, the expected number of dangerous black hole encounters would be something less than 1. You'd most likely watch the entire history of the universe and see nothing of the sort. This is profoundly reassuring. The scenario we've been exploring is not something that is lurking around any imminent corner. It is not a near-future threat. It is one of the most improbable catastrophes that could befall our solar system, far less likely than an asteroid impact, far less likely than a nearby supernova, far less likely than the eventual death of the Sun in about 5 billion years. Yet it is not zero. Probability, no matter how small, is not impossibility, and the galaxy contains roughly 100 billion stellar systems. Across the entire Milky Way, over the entire age of the universe, some small number of solar systems have probably experienced close encounters with wandering compact objects. Those systems, if they harbored life, experienced the kind of catastrophe we've been describing. We simply don't know which ones, and we never will. The search for black holes wandering through the galaxy continues. Projects like the Vera Rubin Observatory's Legacy Survey of Space and Time, the Gaia mission's precise astrometry of stellar positions, and next-generation gravitational wave detectors will progressively improve our senses of compact objects in the solar neighborhood. If there were a black hole on a trajectory toward our solar system, even a very distant one, the accumulating data from these surveys would eventually reveal it. There is one additional category worth mentioning in the context of plausibility: primordial black holes. These hypothetical objects, formed in the early universe, could be much smaller than stellar mass black holes, potentially asteroid mass, or even smaller, and could exist in large numbers. A very small black hole passing through the solar system would be far less gravitationally disruptive than a stellar mass one, and at sufficiently small masses, the effects might be too subtle to detect at all. Some researchers have proposed that a primordial black hole might already have passed through the solar system in the distant past, and that its gravitational influence might be responsible for some of the observed orbital anomalies of distant trans-Neptunian objects. This remains speculative. The hypothesis of a distant Planet 9 provides an alternative explanation for the same data, but it illustrates that the black hole scenario connects to real, ongoing scientific debates about the solar system's structure. Our discussion has focused on stellar mass black holes because they are the most numerous type and therefore the most plausible candidates for a galactic encounter. But let's briefly explore what would happen if the intruder were a different class of black hole entirely. An intermediate mass black hole, perhaps 1,000 to 100,000 solar masses, would represent an incomparably more powerful gravitational disruptor. Objects of this mass are thought to form in globular clusters, dense concentrations of hundreds of thousands of stars that orbit the Milky Way. If a globular cluster's intermediate mass black hole were somehow ejected from its host cluster through gravitational interactions, it could in principle wander through the galaxy. An intermediate mass black hole of, say, 10,000 solar masses approaching our solar system would disrupt it from far greater distances and with far greater thoroughness than a stellar mass intruder. The gravitational influence would be perceptible from light years away. The Oort cloud would be completely dispersed. Every planet in the solar system would have its orbit fundamentally altered. The Sun itself might be captured into orbit around the black hole, becoming a faint companion to an object 10,000 times its mass. The survival prospects for Earth in this scenario are essentially zero for any close encounter. An intermediate mass black hole would not need to come anywhere near Earth to completely demolish the solar system's gravitational architecture. Passing at a distance of a light year would still impose devastating perturbations on the outermost reaches of our planetary system. At the extreme end, a supermassive black hole like Sagittarius A times, with a mass of 4 million suns, would not come wandering through the galactic neighborhood. Supermassive black holes sit at the centers of galaxies, locked in position by the combined gravity of hundreds of billions of stars. They do not wander, however, in the extremely distant future, billions of years, hence the Milky Way and the Andromeda Galaxy are on a collision course. In roughly 4 to 5 billion years, these two galaxies will merge. During the merger, the supermassive black holes at each galaxy's center will eventually merge as well, but long before that, the stellar populations of both galaxies will be mixed and redistributed. The Sun, if it still exists, it will have exhausted its hydrogen fuel and expanded into a red giant before this point. Already consuming the inner planets will be in an entirely different stellar environment, potentially much closer to one of the galactic central black holes. For the purposes of our thought experiment, a supermassive black hole approaching Earth is not a scientifically plausible scenario, but it makes for extraordinary visualization. An object 4 million times the mass of the Sun, with an event horizon roughly the size of the distance from the Sun to Mercury, would be visible to the naked eye from Earth at the distance of the nearest star system, not as a bright object, but as a dark disk blocking starlight behind it, silhouetted against the glow of its accretion disk. Our thought experiment, while based on physics, is speculative in that no black hole is currently known to be approaching our solar system. But the universe has provided real examples of objects experiencing the gravitational consequences of black hole encounters, and studying them gives us confidence in the physics we've described. Tidal disruption events are among the most dramatic real observations of black hole gravitational power. When a star wanders too close to a supermassive black hole at a galaxy's center, the tidal forces exceed the star's own self-gravity. The star is stretched and torn apart, its material flowing into an accretion disk around the black hole. This event releases an enormous burst of radiation, brightening the galaxy's center dramatically for months to years before fading. Astronomers have now observed dozens of tidal disruption events in distant galaxies. They typically produce a distinctive light curve, a rapid brightening, followed by a slower power law decline, and emit strongly in ultraviolet and X-ray wavelengths as the infalling material heats up. Some events are accompanied by jets of material launched perpendicular to the accretion disk at relativistic speeds. These observations confirm the physics of tidal disruption we described for Earth in the most extreme encounter scenarios. The mathematics that predicts stellar disruption is well tested against real observations. Applying it to planetary scales gives us justified confidence in the descriptions we've given throughout this chapter. The star S2, orbiting Sagittarius A times at our galactic center, has been tracked for over 20 years as it completes its 6-year orbit. At its closest approach, it passes within about 120 astronomical units of the supermassive black hole, approximately 3 times the distance to Pluto from the Sunday. The star survives this passage because the tidal forces, while strong, don't reach the disruption threshold for a star at that distance. But the observations of S2 have confirmed multiple predictions of general relativity, including the precession of its orbit and the gravitational redshift of its light. These observations of real astronomical systems give scientists confidence in applying general relativistic physics to hypothetical scenarios like the one we've been exploring. The universe has already run many of these experiments on stars rather than planets, with supermassive rather than stellar mass black holes, but subject to the same physics. Most recently, astronomers have been detecting so-called extreme mass ratio in spirals, compact objects like neutron stars or stellar mass black holes, slowly spiraling into supermassive black holes over millions of years. These events will be primary targets for the LISA space-based gravitational wave detector, planned for launch in the 2030s. Studying them will further refine our understanding of how compact objects move through and interact with massive gravitational environments, the same physics, scaled down, that governs a stellar mass black hole moving through our solar system. Throughout this journey, we've focused primarily on the physics. But the human dimension deserves its own dedicated exploration. How would humanity actually respond to the knowledge that a black hole was approaching the solar system? The response would depend enormously on how much warning time was available. With thousands of years of warning detectable gravitational effects from a distant approaching object, theoretical options would exist for civilizations far more technologically advanced than today's. With decades of warning a closer or harder to detect object, the range of effective responses shrinks dramatically. Let's imagine an optimistic scenario. Humanity detects an approaching stellar mass black hole when it's still several hundred astronomical units away, perhaps 10 to 20 years from significant effects on the inner solar system. What would be the realistic response? The first phase would be scientific, rapid mobilization of every astronomical asset to characterize the threat. What is the black hole's exact mass? What is its precise trajectory? What is the probability distribution of closest approach distances? How much time until various thresholds of impact are reached? The answers to these questions would determine everything that followed. The second phase would be political and social. International coordination of a kind never previously attempted would be necessary. Organizations like the United Nations would be overwhelmed with the task of organizing a response at civilizational scale. Governments would face the challenge of maintaining social order in the face of public knowledge of an existential threat. History does not offer reassuring precedents for how societies handle long-horizon existential threats, climate change being the most relevant modern example, and the record there is mixed at best. The third phase, engineering and preparation, would likely focus on maximizing the survival of human knowledge and genetic diversity in scenarios where Earth itself might become uninhabitable. Accelerated space colonization programs, underground habitats, preservation of seeds and genetic libraries, archives of human knowledge, all of these would become urgent priorities. Some researchers have proposed concepts like black hole arc ships, hypothetical vessels that could be placed in stable orbits around the approaching black hole itself, harvesting energy from the accretion process to support a human colony. This is far beyond any current technology, but the energy available from accretion is truly staggering, and an advanced civilization with sufficient warning time might theoretically exploit it. The psychological and cultural dimension would be equally profound. Art, religion, philosophy, and science would all be transformed by the knowledge of impending cosmic catastrophe. History's examples of societies facing destruction, sieges, famines, wars, show that human responses range from heroic solidarity to complete social collapse. A civilizational scale threat with no possible defense might produce unprecedented combinations of both. Perhaps the most profound human response would be philosophical. For most of human history, we have lived with the implicit assumption that Earth is stable, permanent, a fixed foundation beneath our feet. Even the modern awareness of asteroid impacts and supervolcanic eruptions hasn't fundamentally altered our psychological relationship to Earth as permanent home. A black hole approach would destroy this assumption at the deepest possible level. It would make viscerally real the cosmic truth that Earth is not a permanent fixture but a temporary arrangement, one of billions of planets in a galaxy that has existed for 13 billion years and will continue to transform for billions more. This cosmic humility, forced rather than chosen, might be the most lasting legacy of such an event, even for generations that survived it. We began this journey with a single sentence. Something is moving in the darkness between the stars, and it is heading toward us. We followed that invisible visitor from the far reaches of the Oort cloud, through the realm of the giant planets, into the inner solar system and toward Earth itself. We've seen the comet showers it would trigger, the orbits it would shatter, the tides it would raise, the sun it would perturb, the sky it would transform. And we've arrived at the honest scientific conclusion. This scenario is almost certainly never going to happen to our solar system. The universe is too vast, the galaxy too sparse, the probability too small. In all likelihood, Earth will circle the sun in relative peace until the sun itself begins to expand in about 5 billion years, a fate that is certain but wonderfully distant. But the thought experiment isn't wasted. It never is in physics. By imagining the worst that the universe could throw at us, a stellar mass black hole, the most extreme gravitational object known to exist, entering our cosmic neighborhood, we've learned something important about what makes our solar system precious. The stability of our orbits, the regularity of our seasons, the protection Jupiter provides, the moon's stabilizing influence on our axial tilt, the sun's steady output of energy over billions of years, the extraordinary, improbable combination of factors that has allowed complex life to evolve on this particular planet in this particular solar system. None of these things are guaranteed. The universe is not required to be gentle, but in our corner of the Milky Way, for the past 4.5 billion years, it has been gentle enough. The black holes have stayed away. The rogue stars have not wandered too close. The gravitational architecture of our solar system has held. And in that stability, fragile, improbable, cosmically contingent life has had the chance to emerge from chemistry, to grow in complexity and diversity over billions of years, to eventually produce nervous systems capable of curiosity and minds capable of asking exactly the questions we've been exploring tonight. The black hole is not coming. But knowing what would happen if it did, knowing the physics, understanding the consequences, appreciating the fragility of the conditions that make our existence possible, makes the stability we do have all the more remarkable. We live on a world that orbits a stable star, protected by giant planetary neighbors, stabilized by a large moon, shielded by a magnetic field, wrapped in a life-sustaining atmosphere, a series of coincidences so improbable that it borders on the miraculous. The black holes of the galaxy stay at their vast distances, their gravity too diluted by the incomprehensible scale of space to reach us. For now, and for the foreseeable future, the darkness keeps its distance. And in that darkness, looking up at the night sky, we are safe to wonder,